All right, it is time for another chemistry review video. We are approaching the end of our long equations and moles unit. So I'm recording this on a Sunday. So to my students, I hope you are working as hard as I am on a Sunday. Ready? Okay, the first type of question you will see is mole ratios in formulas. What I want to draw your attention to right here. When you see a chemical formula written like this, and it's a molecule, the subscripts indicate the number of atoms. If you have a mole of the substance, those very same subscripts indicate the moles of atoms in that formula. So subscripts show mole ratios in chemical formulas. Side note, you must always reduce to simplest form. So as an example, here's a chemical formula. What is the mole ratio of hydrogen to oxygen? It's 2 to 4. No, it's not. You have to reduce to simplest form. So that is a wrong answer. 1 to 2. So how do I get there? I divide 2 divided by 2, 4 divided by 2. So the ratio of 1 to 2 is the correct answer.
Okay, this is the section I'm working with, and this is the problem I'm going to help you with. It says, what is the mole ratio of nitrogen to hydrogen in this formula? Okay, so nitrogen and hydrogen are both inside the parentheses. Okay, so inside the parentheses, so let me just show you this two ways. Since they're both inside the parentheses, I have 1 nitrogen inside and 4 hydrogen outside. So the ratio of nitrogen to hydrogen inside the parentheses is 1 to 4. But do you see this 2 outside? Would that affect the ratio if I'm only talking about things in the parentheses? Well, let's find out. That 2 means I have 1 times 2, so I have 2 nitrogen inside, and 2 times 4 is 8. I have 8 hydrogen inside. I would have to reduce this, so divide both of these by 2, and that would give me 1 to 4. So as long as both things I'm comparing are inside the parentheses, I'm okay. But if it was saying compare nitrogen to carbon, for example, I would have to use these numbers. So I'd have to say nitrogen. So if I was doing nitrogen to carbon, okay, nitrogen is 1 inside times this 2, so 2. And carbon only has 1, so it would be 2 to 1. Okay, so if they're both inside the parentheses, I don't have to worry about this subscript. You are going to have to reduce. If I'm comparing elements that aren't both inside the parentheses, I have to worry about that subscript. Okay.
What about mole ratios in equations? Well, the coefficients show mole ratios in balanced chemical equations. So it must be a balanced chemical equation. And again, we always reduce to simplest form. So if you're talking about the ratio of carbon to the ratio of carbon dioxide, it would be 3 to 3. No, it wouldn't. 1 to 1. You have to reduce to lowest terms.
Okay, now I'm looking at this next section, and I'm going to help you with this last problem. So here is the balanced equation, and I'm being asked for a bunch of mole ratios. Okay, now in order to get mole ratios, I need a balanced equation. Well, the good news is the question tells me that it's balanced. I could check 2 times 2 for carbon is 4, 4 times 1 for carbon is 4. Okay, I could go in and check each one, but it already told me it was balanced, so let's not waste our time. So let's look. The mole ratio of C2H6 to CO2. So I need coefficients. So C2H6 is 2 and CO2 is 4. Can I leave it like that? Nope. Remember, simplest form, lowest terms. Divide both of these by 2. So I get 1 to 2. So this answer is 1 to 2. What about the next one underneath? oxygen to carbon dioxide. So in front of oxygen, it is 7. In front of carbon dioxide, it is 4. Can I reduce that? No, I cannot. They have no common factors except for 1. There's nothing I can divide both of these numbers by except for 1 and still keep a whole number. What about O2 to H2O? So in front of O2, we have 7 again. In front of H2O, we have 6. Can we reduce that? No, we cannot. Okay, and then what about C2H6 to H2O? So C2H6 is 2, H2O is 6. Can I reduce this? Yes, yes I can. Divide both of these by 2, and I get 1 to 3. So that is my mole ratio. Now, if you prefer, you can write 1, 2, 3, like with the word. I just always write it like this. This is a correct answer. Okay?
All right, let's talk mass to volume of gases when they're at STP. So remember I gave you this beautiful flow chart. Use it. Use it. It's a great resource. So I'm starting with mass, and I have a gas, and I need to get to right here. I want to know its volume. So I'm trying to get right here. I'm not trying to get over here because this is substance B. That would be switching substances. So if you're using the same substance, you stay on one side. If you're switching substances, you need to cross to the other side. Okay? So if I'm starting with mass and I need to get to volume, I can't skip arrows. So that means I'm going to have to go to moles first. So I need the molar mass. And then I get to volume, and I have to remember this, 22.4 liters in a mole of a gas at STP.
Okay, so now we're on to this next section. I'm going to do this last problem to help you. All right, so how many liters of this gas, and it tells me it's at STP, are present in 45.2 grams of it. So I need to go from grams to liters. If you remember your mole conversion chart, I have grams up here and liters over here. There is no line that goes directly from grams to liters. Essentially, what you should remember is all roads lead through moles, literally, okay? So if I don't have moles, I know I need to get to moles first, okay? So I'm going to write what I was given in the problem and put it over 1. Now, since I'm not switching substances, I'm not going to write the substance, okay? So I'm just going to write 45.2 grams, and I'm going to put it over 1, okay? Now, my next step is I got to get to moles, right? That's the big thing. All roads lead through moles. So I need to get to moles. So how can I change grams to moles? Well, if you look on the back of your reference table, moles I can get with mass and gram formula mass, okay? So that means I need the gram formula mass of C3H8, okay? So I'm going to show you how I do it short instead of writing it down. The gram formula mass of carbon is 12. The gram formula mass of hydrogen is 1. 1 times 8 is 8. 12 times 3 is 36. 36 plus 8 is 44 grams per mole, okay? So I want to put, see, I'm trying to get rid of this gram, so what I want to get rid of, I throw it in the basement. So the grams goes down here, so 44 grams in 1 mole. However, this does not get me to the answer yet, so grams crosses out, that's good. Now I have moles, but I wasn't trying to get moles, I was trying to get liters. And what I need to remember is I have a gas at STP, so I have this magic number, 22.4 liters in 1 mole of a gas at STP. So what unit am I trying to get rid of? Mole. Throw it in the basement. Okay, so what goes on top? Liters. And then, so how do I arrange the number? 22.4 liters per 1 mole. Okay, this is what I used before. So now I'm stuck right here. What do I do? Well, I'm going to multiply across the top. 45.2 times 1 times 22.4. And then I'm going to multiply across the bottom. You will make less mistakes, okay? My moles had canceled out. I'm left with liters as my unit, okay? So this is going to equal something liters. All right, so let's grab our calculator. All right, let's turn this on, and we have to do for across the top. Let's just move this over. There we go. 45.2 times 1. Don't really need to do the times 1, I'm just showing you. Times 22.4 equals. So that gives me 1012.48. Okay. And then look at the bottom. 1 times 44 times 1. Well, that is just 44. So now I need to take this 1012.48 divided by 44 equals 23.010909. This is going to go on forever, you can tell, liters. Now I need to check significant figures. So let's look at this problem real quick. I had 45.2 grams. That's 3 significant figures. So 1 significant figure, 2 significant figures, 3. Look at the next digit. It tells me, don't round that up, please. So my answer, 23.0 liters. And there you go.
Okay, what about mole to mole conversions? Well, now I need a balanced chemical equation, and I'm going to use the coefficient. So I'm going to be starting with moles of a substance, and I want to switch to moles of another substance. That means I need to cross sides. And in order to do that, I need the mole ratio from either the formula, or in this case, what I'm talking about is the balanced chemical equation. So once I do that, I can switch to moles of the other substance.
All right, now I'm on this next section, and again, I'm going to look at this last problem to kind of walk you through this. So let's see, I have a balanced equation, and if it says if 9.5 moles of H2O were produced, how many moles of CH3OH would be required? Now, I'm switching substances. I'm going from H2O to CH3OH. That means in my mole flow chart that I made, we're swapping sides. When we swap sides, we need a mole ratio, okay, from the balanced equation, okay? So let's write what we're given first. Always start there. Since I'm switching substances, I want to keep the chemical formula with whatever I write. So I'm going to write 9.5 moles of H2O, and I'm going to put it over 1. I do the same thing. Whatever I start with, I just put it over 1. It makes the dimensional analysis make much more sense, okay? Now I'm going to multiply it by something. Remember, what I want to get rid of, I throw in the basement. So I don't want moles of H2O anymore. I want moles of CH3OH. So I'm going to throw the moles of H2O in the basement. Can I go from moles of H2O directly to moles of CH3OH? Absolutely I can, because I have a balanced chemical equation. So moles of CH3OH. Okay, so now what do? I need coefficients here. So I need numbers, and they're going to come from the coefficients. So I find H2O, and I just put its coefficient. I find CH3OH, and I just put its coefficient. So what is going to cancel out? This, leaving me with moles of CH3OH, which is what I wanted. So that's good. So how do I solve this math-wise? I take 9.5 times 2 divided by 4, and that is going to give me moles of CH3OH. Okay, so let's do that. 9.5 times 2 equals, divided by 4 equals 4.75 moles of CH3OH. Now, if we were checking significant figures, we only need 2. So 1, 2, look at this next digit. Well, that tells me to round up. So 4.8 moles of CH3OH. And there you have it.
Okay, what about gram to gram conversions? So I have to use moles to get there. So what do I mean? I mean going from grams of one substance to grams of another substance. The equation has to be balanced. I can't do this without a balanced equation. So I would be starting with mass of substance A. And I'm trying to get, so let me bring this up. I'm trying to get right here to mass of substance B. There's no arrow that goes directly between them. So I have to follow the easiest arrow path to get there, and there's only one. So I'm going to go from mass of substance A to the moles of substance A. Then I'm going to use the balanced chemical equation and the coefficients and get to moles of substance B. Then I can finally get to the mass of substance B.
Okay, I'm on this next section for gram to gram conversions, and I'm going to look at this last problem. Okay, so I have a balanced equation, and it says how many grams of LiF will be produced if 45.1 grams of Li2SO3 are used. Okay, I'm going from grams of something to grams of something else. So remember my mole flow chart. I'm going to cross sides. To cross sides, I know I need mole ratios. That's the key to cross sides. So I have grams. I know all roads lead through moles. So the first step is to convert this grams to moles. So I'm going to write what I was given. Okay. Now, since I'm switching substances, I'm going to remember to write the substance with the units. So 45.1 grams of Li2SO3. Put it over 1. That's always how we start. Okay. What do I want to do? I need to get rid of units. The thing I want to get rid of, I throw in the basement. So I need to get rid of grams Li2SO3. How do I know I need to get rid of that? Well, first, it's the only unit I have so far. And second of all, it is not grams of LiF. Anything that is not grams of LiF, we want to get rid of. So remember, what do all roads lead through? Moles. So we need to get to moles. So how do I determine how many grams of Li2SO3 are in a mole? Well, I find, remember, gram formula mass. Okay, so I need to find the gram formula mass for the substance. This time I won't do it right next to it because it kind of made things a little cluttered. So here we have Li2. So this one is probably not one that you have memorized. So you're going to look at your periodic table, right? So I'm going to look right here at Li. Hold on, let me just focus this. Okay, can you see that? There we go. 6.9. So Li is 6.9. Let's check the others before we readjust focusing. Let's look at sulfur, 32.1. And oxygen, we should know, is 16, but let's look. 16. Okay, so now let's readjust our focus. Okay, how many Li's do I have? I have 2. How many S's do I have? 1. And how many oxygens do I have? 3. So that's 48. And that's 13.8. Now what do? I have to add them up. So I have to add 13.8 plus 32.1 plus 48. So let's do that. Let's do 13.8 plus 32.1 plus 48 equals 93.9. So 93.9 grams per mole. So that goes up here. It's grams per mole, so it's 1 mole, and it's 93.9 grams. So that cancels out. But remember, don't forget to write your substance. Okay, is what I'm trying to find moles of Li2SO3? No, it is not. So I'm going to continue. So what do I want to get rid of? Throw it in the basement. I don't want moles of Li2SO3. Here's where I can swap substances. What substance in this equation am I trying to get to? Moles of LiF. Finally, okay, this will allow me to cross this out. How do I determine what numbers go here? Just look at the coefficients in the balanced equation and plug in the numbers. So it's 6 for LiF and 3 for Li2SO3. Is what I was trying to find moles of LiF? No, it was not. It is grams of LiF. So again, we need gram formula mass, okay? So I need it for LiF. Well, Li, we already knew, was 6.9, so we just have to look up F. Okay, so right here, which is going to be just 19. So then I'm going to add 19 and 6.9. 19 plus 6.9 equals 25.9 grams per mole. So what do I want to get rid of? Throw it in the basement. Moles of LiF. I'm trying to, I have units to go to grams of LiF. It's 1 mole and it was 25.9. This cancels out. I'm left with grams of LiF. Is that what I wanted? Yes, finally. Okay, so now I have this whole mess looking thing. So what I recommend doing is rewriting this so I have everything multiplied across the top and everything multiplied across the bottom. So 45.1 times 1 times 6 times 25.9 equals, and on the bottom, 1 times 93.9 times 3 times 1. Now in reality, do I need to worry about the times 1? No, but I just want to see, I want you to see where it's coming from. So now I need to do those in the calculator. So I need to do 45.1 times 1. I'm just going to multiply everything times 6 times 25.9 equals, I'm going to put that on the top. So 7008.54. And then on the bottom, we have 1 times 93.9 times 3 times 1 equals, and we're going to write that on the bottom. Okay, now I have to divide those two. So let's do 7008.54 divided by 281.7 equals, so I get 24.879446, okay, grams of LiF. Let's see what our significant figure should be. So here was back to my equation. I had 3 significant figures in my problem. So 1, 2, 3. Look at that. A 7 says round up. So 24.9 grams of LiF. And there you go.
Okay, balancing equations, big rule to remember, only change coefficients. You were given this guide indicating a good strategy is listing the elements, how many you have, what coefficients you're adding, okay? And the total atoms have to be the same on both sides, okay? You have to reduce the coefficients to the lowest whole numbers if possible. Remember, odd, even pairs are a good place to start. Putting a 2 in front of the most complicated looking formula is a good place to start. Don't start with single atoms, start with compounds, okay? So those are some good strategies.
Okay, our first help with balancing is with synthesis. Remember, synthesis means one product, 2 or more reactants. You're building something bigger. So all you do, look in the product side. One thing, one thing, one thing. Synthesis, okay? So we're going to balance this one in particular. So what elements do I have? Ag and S, okay? And I'm going to look at how many I have on each side. So on this side I have 1, on this side I have 8, on this side I have 2, on this side I have 1. Okay, well, nothing is balanced. So where do I start? Okay, well, let's test something. So if I put I could do this. I could start here. I could do times 2. That would mean to put a 2 right here. Okay, well, that didn't help my sulfur, right? So let's balance sulfur. So I got to do times 8, right? So when I put this 8 here, it also changes the Ag, which means now that coefficient doesn't work. I got to try a new coefficient. So I'm going to multiply it by 16. So 16. So now I have Ag 16 on this side, 16 on this side, 8 on this side, 8 on this side. So correctly it is 16 Ag plus 1 S8. Remember, this is where the blank was. So if the blank stresses you out, you can write the 1. Yields 8 Ag 2S. There you go. Okay, our next type of reaction is decomposition. This is the opposite of synthesis. You're breaking something down. So you're starting with one thing and breaking it apart. So here's the one that we're going to look at. I'm going to make my list of elements. So on the reactant side, I have Na, Cl, and O. On the product side, I have the same elements. If I didn't, that would be alarming. Okay. Now let's look at our numbers. So we have 1, we have 1, we have 3. We have 1, we have 1, we have 2. Okay, well, Na is balanced, Cl is balanced, so let's look at O. This is an odd even pair. When you have something like this, start with the odd one. Also, note, this oxygen is in a formula, so starting here is a better idea than starting over here. Okay, so times 2, 3 times 2 is 6. So what coefficient do I write? The 2, what I multiplied it by. So when I put a 2 there, it doesn't just change the O, it changes Na and it changes Cl. So now let's see if I can resolve everything over here. So I need 2 NAs, right? When I put the 2 in front of the Na, it also changes Cl. Okay, so those are fixed. Let's see if we can fix O. I need 6. So times 3 is 6. The 3 goes in front of the O, and there you go. All right, so one thing I do want to mention right here, this was my original formula, and I needed to fix the O. You cannot do this. You cannot just squeeze a 2 in there as the coefficient. You cannot put a coefficient in the middle of a chemical formula. A coefficient can only go in the front of a chemical formula. Now, it may look like, say for example, I had this. It may look like there's a coefficient in the middle of the formula, but you see this means this hydrate, that water is attached here. So the 2 is in front of the H2O, not in the middle of the formula. Okay? So you can never, ever, ever put a coefficient in the middle of a formula. Okay, for this next one, I'm going to do single displacement or single replacement. The way you can tell it's single displacement or single replacement is you see a single element on one side and then a different single element on the other side. That's the clue. All right, so I need to make my list of elements. I have Mg, and then I have Sn, N, and O. Over here I have Sn, Mg, N, and O. I have the same elements, okay, which you have to. So magnesium 1, tin is 1. Nitrogen, I have to multiply by the subscript, so that's 4. Oxygen is 12. On this side, 1, 1, 2, and 6. 2 times 3. So, well, I need to start somewhere. So let's start with this O. Okay, in order to balance the O, I am going to, over here, need to multiply it by 2, correct? So times 2 equals 12. This 2 has to go in front of the O. I can't put it right here because remember, you can never, ever, ever put a coefficient in the middle of a formula, so it has to go here. When it goes there, it changed magnesium and it changed nitrogen. Well, the nice thing is it fixed the nitrogen for me. Okay, SN, tin is still okay, but look at magnesium, 2 and only 1. So I have to multiply this magnesium times 2. 2 magnesium, 2 magnesium, 1 tin, 1 tin, 4 nitrogen, 4 nitrogen, 12 oxygen, 12 oxygen. We're balanced. We can leave these lines blank or put a 1. All right, for double displacement, I have 4 compounds. The cation switch places. Basically, I have compound, 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 compound. Oh my goodness, so many compounds. That's how you can tell. So let's do the example we have here. Let's write my list of elements: Ba, N, H, and F. Over here, it's Ba with F and then N with H. Writing it like this just helps me keep straight which elements are in which formula. Ba has 3, N has 2, H has 1, F has 1. On the other side, Ba has 1, F has 2, N has 1, H has 3. Okay, well, literally not a single thing is balanced. Okay, so we have to start somewhere. So, all right, I'm just going to start with barium. So barium, I have to multiply times 3 is 3. When I put the 3 here, it doesn't just change barium, it also changes fluorine. So times 3 is 6. Okay, so barium is balanced. Let's fix fluorine. Okay, times 6 is 6. This 6 can't go directly in front of fluorine. It's got to go on the line right here, which means it also affects hydrogen. Times 6. All right, so fluorine is okay, barium is okay. Hydrogen, now that's messed up. So let's try and fix hydrogen. Times 2 is 6. The 2 needs to go in front of the hydrogen, but not in the middle of the formula, in front, which means it also changes nitrogen, which means actually it fixed nitrogen. So let's check. 3 barium, 3 barium, 2 nitrogen, 2 nitrogen, 6 hydrogen, 6 hydrogen, 6 fluorine, 6 fluorine. I have 1 blank. I can leave it blank, or I can write a 1. Remember, never, ever, 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 ever write a 0. Essentially, you would erase it if you did. So don't do that. All right, and our last type of equation of balance is combustion. We can tell something is combustion because we have oxygen as one of our reactants, and we have carbon dioxide and water as our products. Okay, so this is carbon dioxide. That's just a little typo, so just adjust that right now. So oxygen as a reactant, water and carbon dioxide as products. Okay, let us make our list of elements. We have C, H, and O. And on this side we have H, O, and then we have C and O again. And those 2 O's we're going to have to add to total. So carbon I have 6, hydrogen I have 6, oxygen I have 2. Hydrogen I have 2, oxygen 1 right here, and then carbon I have 1, and I have 2 oxygen there. So my total oxygen right now is 3. So yeah, nothing is balanced. My tip for balancing combustion reactions is start by putting a 2 in front of this right here. I like to start there. It usually helps resolve everything. It's tough to decide where to begin, so that's just a good place. So if I put a 2 there, okay, then that means this carbon is times 2 and this hydrogen is times 2. Now I'm going to see if I can resolve the carbon and the hydrogen over here next. Okay, so hydrogen had 2, so let's multiply it by 6. So when I put the 6 there, it changes this oxygen. Okay, so right now that's not right. That would be 6 plus 2, that's 8. And then I'm going to resolve the carbon, so that has to be times 12. when I put a 12 there, it also affects that oxygen. So that's times 12. So this is no longer 8. 6 plus 24, I have 30. Okay, so carbon is still balanced here. Hydrogen is still balanced, but oxygen, oh my goodness, there's 30 on this side and only 2 over here. So I'd have to do times 15, it's 30, and look at that. I'm balanced, 12 carbon, 12 carbon, 12 hydrogen, 12 hydrogen, 30 oxygen, 30 oxygen. Let's look at our coefficients. 2 to 15 to 6 to 12. Can this be reduced? No, it's actually balanced. Sometimes when you do this, you end up having to divide all the coefficients by 2, but not in this case. We're finished.
Okay, we can use the values in table I for some heat calculations. So here at the bottom, remember, it tells you a minus sign indicates exothermic reaction. But for example, this reaction for potassium nitrate being dissolved in water, it absorbs 34.89 kilojoules of heat. Well, that's when one, because there's no coefficient here, that's when 1 mole dissolves. What if 2 moles dissolved? Well, I would just multiply this number by 2. What if 3 moles dissolved? Well, multiply that by 3. What if it was 1.64 moles of this? Well, I'd multiply that by 1.64. Easy enough.
All right, I am on this section right here. I'm going to help you with these 2 problems. For these 2 problems, you absolutely have to look at table I. Okay, so first, the first one says, how many kilojoules of heat are absorbed when 34.41 moles of NO2 gas are formed? So what I have to do, when it says formed, I'm looking for the product side. So I'm scrolling down to find NO2 gas. Oh, here we go. So when I look across from this equation, I see plus 66.4. So I'm just going to write that down, plus 66.4. And remember, the units up here, it's in kilojoules. All right, so how many kilojoules of heat are absorbed when 34.1 moles of NO2 gas are formed? Well, let's look at this equation. Again, here it is. It's 66.4 kilojoules, and look how many moles of NO2 are formed. 2. So 66.4 kilojoules for every 2 moles. Okay, so let's write what I was given. That's all, we always start a problem. So I was given 34.1 moles. I put it over 1. What do I want to get rid of? Throw it in the basement. I want to get rid of moles. And what am I trying to find? Kilojoules of heat. So what did my equation tell me? Well, it said I got 66.4 kilojoules of heat, but that was not for 1 mole, that was for 2 moles. So again, how did I know it was for 2 moles? Look at the equation. The coefficient in front of NO2 was 2. All right, so that is for every 2 moles. So that moles will cancel out. It will leave me with kilojoules. So how do I solve this? I do 34.1 times 66.4 divided by 2, and that is going to give me an answer in kilojoules. So let's see what we get. So I have 34.1 times 66.4 equals divided by 2. 1132.12 kilojoules. Let's go back to my problem. I had 3 significant figures, 1, 2, 3. The 2 says don't round up, so I do this, but I'm not done. See, here's where the decimal point is. Every digit up until the decimal point has to be replaced with a 0, because 1,132 would not round to 113. That would make no sense. All right, so let's try another example, and that's this second one. All right, So how many moles of HI gas are formed when 322 kilojoules of heat are absorbed? So again, I need to find the correct equation. I'm forming HI, okay? Hydrogen and iodine. Okay. Here we go. So it has a 2 coefficient in front of it, and it says plus 53.0. So it's 2 moles and 53.0 kilojoules. So I just need that so I can set up my problem. So I have 322 kilojoules of heat. My given, put it over 1. What do I want to get rid of? Throw it in the basement. Kilojoules. I want moles. So what is my conversion? For every 53.0 kilojoules, I'm going to get 2 moles. So again, to remind you of how I got to that 2 moles, the coefficient in front of HI is a 2. Okay, so now how do I solve this? 322 times 2 divided by 53.0. Remember, I can leave this one off. If that stresses you out, you can write that. So let's do this math and see what I get. 322 times 2 equals, divided by 53 equals 12.1509434 moles. Let's check significant figures. 1, 2, 3 in my problem. 1, 2, 3. 5 tells me to round up. 12.2 moles. And there we go.
Oh, sometimes you are given a balanced equation and you're asked to find a missing formula. It could be on the reactant side, could be on the product side. You don't know. So what you have to do is you have to count the atoms, determine which elements and how many atoms of each element are missing, check to see if that formula has a coefficient in front of it, and then you're going to write the chemical formula. You'll see when I go through the steps.
Okay, we're on the last one, identifying a missing reactant or a product. So this equation is balanced already. The only thing that's here is there's a missing formula. So let's see if we can figure it out. So here's my divider for my arrow. I have K, I have C, I have O, and then I have another O. On this side, I have C and I have O. So let's count. So far on this side, remember these coefficients matter, so now I have to look at the coefficients. So the carbon is 2, the oxygen is 4, 2 times 2. The potassium is 4, the carbon is 2, the oxygen is 6, and this oxygen is 6. So my total number of oxygen is 12. 6 plus 6. Okay. So let's look at what's missing. Well, carbon and carbon is fine, okay? But I have 4 potassium over here and none, right? Over here I have 4 oxygen. Over here I have 12 total oxygen. So I need to have 4 potassium on this side. And I need to have 8 more oxygen, right? So like this, I need 4 potassium, I need 8 oxygen. So you would think you would write just K4O8 and be done. But you're not. Check the equation. Look at this. See this coefficient in front of here? Okay, so if I put a 4 in front of this, well, that would really mess everything up. I'd have 16 potassium, which is not what I have. So since this coefficient is in front of the formula, that's not the right formula. So how do I find the right formula? Well, I can start with that. How do I know it was this? Because I had 4 potassium missing and 8 oxygen missing, okay? But my coefficient of 4 in front means these subscripts are going to be divided by 4. So it's going to be KO2. And there we go.
Okay, in this last section, it is not on your sheet, but I do want to talk about it because it's another thing that you can do with this mole chart. We can go from liters of one substance to liters of another substance, but they both must be gases and they both must be at STP. So the reaction has to be happening at STP. We need a balanced equation. So how are we going to get here? Well, there's no arrow that goes directly. That would be nice if it did, but there's not. So I have to go step by step. So I'm going to go first to moles of the first substance, use the balanced equation to get moles of the second substance, and then I can get to the volume of the second gas. That's how you do it.
All right, and we are on our last problem. So you are given this equation, this piece of information, and you need to find this. So again, remember from our giant mole conversion chart, you can only swap sides because I'm going from chlorine to nitrogen when I do moles. So all roads lead through what? Moles. So let's write what I was given. And remember, since I'm switching substances, make sure I keep the substance with the number and the units. So I have liters of chlorine. Put it over 1 like usual. Then remember, what do I want to get rid of? Throw it in the basement. I want to get rid of liters of chlorine. And all roads lead through what? Moles. So how do I know how many liters and moles with chlorine? Well, you have to remember that 22.4 liters in 1 mole, because this problem told you it was a gas at STP. All right, so that allows me to cross out liters of Cl2. Now I have moles of CO2. Remember, once I have moles, I can convert to a new substance. So what do I want to get rid of? Moles of Cl2. So where do I put it? Throw it in the basement. And now I'm going to convert to moles of N2. How do I get the numbers? Well, look at my balanced equation and I just put the coefficients. So in front of Cl2 I have a 3, in front of N2 I have a 1. So that leaves me able to cross out moles of Cl2. Was I finding moles of N2? Nope, liters of N2. So what do I want to get rid of? Moles of N2, throw it in the basement, and I want to get liters of N2. How do I do that? Use that conversion factor again. But remember, the 22.4 goes with the liters. Okay? Now I cancel this out. I'm left with liters of N2. Is that what I wanted? Sure is. So how do I solve this? 17.2 times 1 times 1 times 22.4. divided by 1 times 22.4 times 3 times 1. Now, I could save myself a little bit of time. I could multiply across the top, multiply across the bottom. Easy, right? I should realize I don't have to worry about the ones. Also, I have a 22.4 on the top and a 22.4 on the bottom, so those cancel out, right? The ones, so I'm left with 17.2 on the top divided by 3. Well, look at that. All right, so then I'm going to turn on my calculator, do 17.2 divided by 3 equals 5.73333 liters of N2. So let me just show you, it would be the same if I hadn't done that. So if I just did 17.2 times 1 times 1 times 22.4 would equal 385.28. And across the bottom, 1 times 22.4 times 3 times 1 equals 67.2. Oops. And then if I did 385.28 divided by 67.2, I would get literally what I got just here. So that was just faster. Now I just check significant figures. I was given this number, so I need 3. 1, 2, 3. Look at the next digit. I do not round up, so 5.73 liters of N2. And voila, there you go.
Okay, phew, that was a lot. This was the next set of problems to guide you through this difficult unit of equations and moles. So between this video and the last problem help video I made, it covers pretty much all of the content from this unit. So good luck, and I hope you learned something.